Right now, you are looking at something. Maybe it is a screen. Maybe it is a wall, a window, a ceiling. Whatever it is, the light reaching your eyes left its source a moment ago, traveled through the air between you and the object, and arrived at your retina in a process so fast and so continuous that you have never once had reason to question it. You see things as they are. You see the present. That is the assumption you carry through every waking moment of your life, and it has never failed you in any way that mattered. But it has always been wrong. The light from a lamp across the room takes nanoseconds to reach you. The light from the sun takes 8 minutes. When you look at the sun, you are not seeing the sun as it is. You are seeing the sun as it was 8 minutes ago. If it had vanished at that moment, you would not know for 8 minutes. You are always looking into the past. Every observation you have ever made of anything beyond arm's reach is a message from a prior moment, transmitted at the speed of light, arriving slightly late. This is not a philosophical caveat. It is the literal physics of how vision works, of how all observation works, of how the universe conveys information from one point to another. Now, extend this principle outward to the nearest star, Proxima Centauri, 4.2 light-years away. The light you see from it tonight left it 4.2 years ago. To the Andromeda Galaxy, 2.5 million light-years away. The light arriving from it now has been traveling since before our species existed. To the most distant objects ever observed, galaxies so far away that their light has been traveling for more than 13 billion years, and released when the universe was a fraction of its current age, stretched and dimmed and been redshifted by the expansion of space itself into a faint signal that requires the most sensitive instruments ever built to detect. Those instruments now exist. The James Webb Space Telescope, launched in December 2021 and fully operational since mid-2022, is the most powerful astronomical observatory ever deployed. Its mirror is 6 times larger in area than its predecessor, the Hubble Space Telescope. It observes primarily in the infrared, allowing it to see through clouds of dust, the block visible light, and to detect the faint, red-shifted emissions of objects so distant that their light has been traveling since near the beginning of time. Its detectors are cooled to within a few degrees of absolute zero to minimize thermal noise. It was designed to see the first stars and the first galaxies, to look back to the edge of the observable universe, to answer questions about the earliest epochs of cosmic history that no previous instrument could approach. And it has found something that was not expected. Not one thing, not a minor anomaly, a pattern of observations accumulating across different teams, different fields, different instruments and methods that does not fit within the current based understanding of how the universe formed and evolved. Galaxies that should not exist, at distances where they should not be, with properties that no current model of galaxy formation predicts. A tension in the fundamental measurement of the universe's expansion rate that is not resolved as the data has improved. Evidence for structures at the largest scales that challenge the assumption of uniformity that underlies the standard cosmological model. And most recently, individual objects, specific targets observed in extraordinary detail. The display properties with no satisfying explanation within existing theoretical frameworks. These are not measurement errors. They have been checked They have been cross-verified with independent instruments and methods. The James Webb Telescope has not produced a list of things it expected to find. It has produced a growing list of things that should not be there, things that are there anyway, and things that imply, if taken seriously, that the universe is structured differently, evolved differently, and operates by rules we have not fully mapped. This video is about what the telescope has found and what it means. It is not about science fiction scenarios or speculative horizons. Everything described here is grounded in published data, peer-reviewed analysis, and theoretical frameworks taken seriously by the scientific community. The unease you will feel is not manufactured. It is the natural consequence of what the observations actually say. The core question is this: if the universe we observe through the most powerful instrument ever built does not match the universe our best theories predict, what does that tell us about the theories, about the observations, and about the nature of the reality that both are trying to describe? There is no resolution at the end of this. There is only the evidence, and what the evidence requires you to consider. Begin. A telescope built to see the beginning. The James Webb Space Telescope was conceived in the 1990s, approved in 1996, and spent more than 2 decades in development before its launch on December 25th, 2021. Its journey to the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth on the sun-facing side, took approximately a month. Its commissioning, the complex process of aligning its 18 hexagonal mirror segments into a single coherent optical surface, and calibrating its 4 scientific instruments, took 6 months more. The first full-resolution science images were released in July 2022. They were immediately recognized as the deepest and most detailed views of the universe ever captured. And understanding what the telescope is and how it works is necessary to understanding why what it has found is significant. The James Webb Space Telescope, or JWST, is a reflecting telescope with a primary mirror 6.5 meters in diameter, composed of 18 gold-coated beryllium hexagons that fold for launch and unfurl in space. Its collecting area is approximately 6 times that of the Hubble Space Telescope, giving it a corresponding advantage in sensitivity. More importantly, it observes primarily in the near-infrared and mid-infrared portions of the electromagnetic spectrum, wavelengths longer than visible light, ranging from 0.6 to 28 micrometers. The choice of infrared observation is not incidental. It is the key to the telescope's scientific mission. The universe is expanding, and the expansion stretches the wavelengths of light traveling across it. Light emitted in the ultraviolet or visible range by objects in the distant universe is stretched by the time it reaches us into the infrared. An object at a redshift of 7, meaning its light has been stretched by a factor of 8, emits visible light that arrives at Earth as near-infrared radiation. To see the most distant objects in the universe, you must observe in the infrared. The Hubble Space Telescope's limited infrared sensitivity left the most distant universe largely inaccessible. JWST was designed specifically to fill that gap. The telescope's 4 scientific instruments cover different portions of the infrared spectrum and different observational modes. The near-infrared camera NIR cam, is the primary imaging instrument, covering wavelengths from 0.6 to 5 micrometers. The near-infrared spectrograph, NIR spec, can simultaneously take spectra of up to 100 objects at once, measuring the precise wavelengths of light emitted or absorbed by each. The mid-infrared instrument, MIRI, covers 5 to 28 micrometers and is the most sensitive mid-infrared instrument ever placed in space, cooled to approximately 7 Kelvin. The fine guidance sensor and near-infrared imager and slitless spectrograph, NIRIS, provides additional spectroscopic and imaging capabilities. Together, these instruments give JWST an ability to observe the universe across a range of distances, temperatures, and physical processes that no previous facility could approach. It can detect the infrared glow of galaxies forming in the first few 100 million years after the Big Bang. It can take spectra of the atmospheres of planets orbiting nearby stars. It can image the dust and gas within stellar nurseries in our own galaxy in detail that reveals individual protostars. It can study the environments of active galactic nuclei and the dynamics of galaxy mergers across cosmic time. The telescope was expected to extend human knowledge at all of these frontiers. It has done that. But it has also, in doing so, revealed that the frontier is not where the maps said it would be. The boundaries of the known universe, as defined by the best theoretical models in place at the time of the telescope's design, have not simply been pushed outward by the new observations. They have been complicated. Objects are appearing in places they should not be, with properties they should not have, at abundances that the models do not predict. What follows is not a catalogue of the telescope's greatest images. It is an account of the places where the telescope looked, expected to confirm what the models predicted, and found something else. Those places are where the interesting physics lives. And the interesting physics, as the data accumulates, is becoming increasingly interesting in the specifically uncomfortable way that good science produces, not by answering questions cleanly, but by revealing that the questions were more complicated than anyone knew how to ask. The galaxies that should not exist. In the standard model of cosmology, the lambda cold dark matter model, the earliest galaxies formed gradually, beginning as small clumps of dark matter that gravitationally attracted gas, which cooled and condensed into the first stars. These early structures then grew over billions of years through mergers and accretion, building larger and more massive galaxies over time. The process is hierarchical. Small things form first, large things form later, and the most massive and most structured galaxies are expected to be relatively recent in cosmic history. The early universe, the universe as it was in the first few 100 million years after the Big Bang, should be populated by small, irregular, relatively faint, and low-mass proto-galaxies, the seeds from which today's massive spiral and elliptical galaxies eventually grew. JWST began observing in this early universe regime almost immediately after commissioning. In its first year of operation, using deep field imaging and spectroscopic follow-up, it detected hundreds of galaxy candidates at redshifts greater than 10, corresponding to objects as they appeared less than 500 million years after the Big Bang. This was expected. The telescope was designed to find these objects. What was not expected was their properties. The galaxies detected at these extreme distances are in many cases far more massive than the models predict. Several objects identified in the first year of JWST observations have stellar masses estimated at 10 to the power of 10 or even 10 to the power of 11 solar masses, meaning they contain as many stars as our Milky Way or more. These masses were inferred from the brightness and color of the objects, accounting for the known physics of stellar populations. The inferences are not certain. They depend on assumptions about stellar populations and dust attenuation that carry systematic uncertainties, but the values are so much larger than model predictions that even with generous error bars, a significant tension remains. The problem can be stated simply. In the standard model, the universe at a redshift of 10 is approximately 500 million years old. Building a galaxy with 10 to the power of 11 solar masses of stars in 500 million years requires an extraordinary rate of star formation, sustained with very high efficiency for the entire available time. The models of galaxy formation do not produce galaxies this massive, this early. The dark matter halos that host galaxies of this mass form slowly through gravitational clustering. The gas that fuels star formation takes time to cool and condense. The feedback processes from supernovae and active galactic nuclei, which in the models limit star formation efficiency by heating and expelling gas, should prevent the rapid, efficient star formation that would be needed. The tension is quantitative. Studies using JWST's first deep field data, published in late 2022 and early 2023, found that the abundance of massive, early galaxies, the number of them per unit volume of space, exceeds the predictions of standard galaxy formation models by factors of 10 to 100, not slightly more than expected, an order of magnitude or more above the predicted number. This discrepancy is large enough that even the most generous interpretation of the systematic uncertainties does not make it disappear. Something is producing massive galaxies in the early universe far more efficiently than the standard model says should be possible. The possible explanations include modifications to the galaxy formation process, such as higher star formation efficiencies or reduced feedback from supernovae and active galactic nuclei in the early universe. They include modifications to the dark matter model, such as different assumptions about how dark matter halos formed and grew in the early universe. They include the possibility of systematic errors in the mass estimates, though multiple teams using different methods continue to find the same excess. And they include, for the theoretically daring, modifications to cosmology itself, to the assumptions about how the universe expanded and what it contained in its earliest epochs. None of these explanations is currently confirmed. All of them are being actively investigated. The tension has not gone away as the data has improved. It has, in many cases, sharpened. The galaxies that should not exist are there in the data, awaiting an explanation that no one has yet provided. The Hubble tension and what it means that it has not gone away. There are two ways to measure the rate at which the universe is expanding. The first uses nearby objects, calibrating distances through a chain of standard candles, objects of known intrinsic brightness that extends from our own galaxy to the distant universe. The second uses the cosmic microwave background, the radiation left over from the early universe, which encodes information about the expansion rate at a time when the universe was approximately 380,000 years old. The two methods should agree. They measure the same quantity. The laws of physics that govern the universe are not expected to be different at different times or in different places. They do not agree. The measurement using nearby objects, primarily type 1, a supernovae calibrated through a distance ladder that begins with Cepheid variable stars, gives a Hubble constant, the current expansion rate, of approximately 73 kilometers per second per megaparsec. The measurement using the cosmic microwave background, specifically the Planck satellite data, fitted to the standard lambda CDM cosmological model, gives a Hubble constant of approximately 67 kilometers per second per megaparsec. The discrepancy is approximately 8%. It has been present in the data for years. It has not resolved as the measurements have improved. It has in many cases strengthened. This is known as the Hubble tension, and it is one of the most debated problems in contemporary cosmology. Before JWST, the most natural explanation was measurement error, specifically the possibility that the distance ladder used to calibrate the nearby measurement contained systematic errors that propagated to a biased estimate of the Hubble constant. The Cepheid variable star calibration at the base of the ladder was the primary suspect. If the Cepheid distances were systematically wrong by a few percent, the entire ladder would be off and the two measurements might be brought into agreement. JWST was used to test this possibility directly. In 2023, a team led by Adam Rees, one of the discoverers of the accelerating expansion of the universe, used JWST to measure Cepheid variable stars in nearby galaxies with unprecedented precision. The goal was to determine whether crowding effects, the blending of light from multiple stars in the dense stellar fields observed by Hubble, had caused systematic errors in the Cepheid distance measurements. JWST's superior resolution could separate individual stars in these fields where Hubble could not, allowing a direct comparison. The result was not reassuring. The JWST Cepheid measurements confirmed the Hubble-based values to within the measurement uncertainties. The Cepheid distances were not significantly in error. The distance ladder, rechecked with the most precise instrument available, continued to give a Hubble constant of approximately 73. The tension with the CMB-based value of 67 was not resolved. It was confirmed. This matters because it implies one of several possibilities, none of them comfortable. The standard cosmological model, which the CMB measurement uses to infer the Hubble constant, may be wrong in a specific way that affects the high redshift measurement, but not the low redshift one. There may be new physics in the early universe, a different form of energy, or a different behavior of dark energy that modifies the expansion history before the CMB was formed. There may be unknown systematic errors in the CMB analysis that have not yet been identified, or the tension may be pointing towards something genuinely new, a modification to cosmology itself that no one has yet formulated in a satisfying way. The Hubble tension, confirmed rather than resolved by JWST, is not a minor discrepancy. An 8% disagreement between two precision measurements of the same fundamental constant of the universe is a substantial scientific problem. It has persisted for years, survived multiple cross-checks, and resisted every proposed resolution. JWST was the most powerful tool available to test one of the most plausible explanations. The test was performed. The explanation was ruled out. The tension remains. The first light problem. Stars before they should exist. The first stars in the universe, known as population 3 stars, occupy a special place in theoretical astrophysics. They are the first structures complex enough to be called stars, regions of gas that became dense enough to ignite nuclear fusion, converting hydrogen and helium into heavier elements for the first time. Before them, the universe contained only hydrogen and helium and traces of lithium, the products of Big Bang nucleosynthesis. Every heavier element, every carbon atom, every oxygen atom, every iron nucleus in your body was produced in a star or in the explosion of a star, and the population 3 stars were the factories that began this process. In the Standard Model, population 3 stars formed in the first few 100 million years after the Big Bang, in dark matter halos where primordial gas cooled and collapsed. They are expected to be massive, hundreds or even thousands of solar masses, because the primordial gas lacked the heavy elements that allow gas to cool efficiently at small scales. Without efficient cooling, the gas collapses only at large scales, producing massive stars. These stars lived briefly, exhausted their fuel in millions rather than billions of years, and exploded as supernovae, seeding the universe with the first heavy elements. Their direct observation has been a primary goal of JWST because they are too faint and too distant for any previous telescope to detect. JWST has not yet definitively confirmed the direct observation of an individual population 3 star. The distances involved are enormous, the objects are extremely faint, and distinguishing a single population 3 star from a very faint early galaxy is observationally challenging. But JWST has found objects whose spectroscopic signatures are consistent with the presence of population 3 stars within them, or with stellar populations that contain elements only in the abundances expected from the earliest epochs of star formation. What it has also found, in observations of extremely distant galaxy clusters acting as gravitational lenses, are individual stars whose properties are consistent with population 3 characteristics: massive, extremely hot, and metal poor. These detections are tentative, requiring confirmation, and the identifications carry significant uncertainties, but they represent the first plausible candidates for population 3 star observations, and their presence at the distances and abundances suggested by the data is creating new constraints on the first light epoch that the models were not designed to accommodate. The deeper issue is not the individual detections. It is the overall picture of early star formation that JWST is assembling, the rate at which the first stars formed, the efficiency with which the first dark matter halos collapsed into star-forming systems, and the chemical enrichment history of the early universe as inferred from the spectra of early galaxies are all pointing toward a universe that was more active, more structured, and more chemically evolved in its first billion years than the standard models predict. The first light problem is not simply a problem of observing the first stars directly. It is a problem of reconciling the entire early star formation history with what current models say should have been possible in the available time. The models were built on assumptions about dark matter, clustering rates, gas cooling physics, feedback processes, and cosmological parameters that seemed well motivated and well tested at lower redshifts. JWST is probing the regime where these assumptions were never directly tested, and the probe is finding discrepancies. The first light arrived earlier than expected, burned brighter than expected, and left a chemical signature in the early universe that is richer than the models foresaw. The implications of this are still being worked out, but the working out is happening against the background of data that does not wait for theory to catch up. The impossible brightness of early quasars. At the center of almost every large galaxy lies a supermassive black hole. In most galaxies, including our own, this black hole is relatively quiet, consuming little material and emitting little radiation. But in a subset of galaxies, the central black hole is actively accreting large amounts of gas, heating it to extreme temperatures, and generating luminosities that can outshine the entire galaxy by factors of thousands. These objects are called quasars. They're from quasi-stellar objects because they appeared in early observations as point-like sources resembling stars, but with spectra showing extreme redshifts that indicated cosmological distances. Quasars are among the most energetic and most distant objects ever observed. The central black holes powering quasars, called quasar-host black holes or supermassive black holes in their active phase, can contain masses of millions to billions of solar masses. The mass contained in a black hole constrains how quickly it could have grown. Black holes accumulate mass through accretion, and there is a maximum rate at which a black hole can accrete gas, called the Eddington limit, set by the balance between the gravitational pull inward and the radiation pressure from the accreting material pushing outward. If a black hole accretes at the Eddington limit continuously from some initial seed, the maximum mass it can reach in a given time is calculable. Before JWST, the most distant known quasars existed at redshifts of approximately 6 to 7, corresponding to a universe approximately 700 to 800 million years old. These quasars already posed a theoretical challenge, because their central black holes had masses of billions of solar masses that had to accumulate in less than a billion years from whatever seed black holes existed at earlier times. Forming billion solar mass black holes, this quickly requires either continuous Eddington-limited accretion from very massive seeds, or episodes of super Eddington accretion, or both. Neither is straightforwardly accommodated by standard models. JWST has now detected quasar-like objects at redshifts exceeding 10, corresponding to a universe less than 500 million years old. The central black holes in these objects have masses estimated at hundreds of millions to billions of solar masses. The mass problem is now more severe than it was before, because the available time for growth is shorter and the required masses are comparable. How a black hole grows to 10 to the power of 9 solar masses in less than half a billion years, starting from a stellar mass or even an intermediate mass seed, requires either a mechanism not present in the standard model or an initial seed mass far larger than any currently confirmed observation supports. The implications of this go beyond the specifics of black hole growth. The supermassive black holes influence their host galaxies through the radiation and outflows they produce during their active phases. The timing and manner of this influence, called AGN feedback, is a central element of galaxy formation models. It is the mechanism by which models prevent the formation of galaxies more massive than those observed, by heating and expelling gas that would otherwise form stars. If supermassive black holes were in place earlier than the models predict, AGN feedback was also operative earlier, and its effects on the galaxy population at high redshift are different from what the models assume. The chain of consequences extends further. Early quasars ionize the gas around them, contributing to the reionization of the universe. The epoch during which the neutral hydrogen that permeated the cosmos after the CMB epoch was ionized by the first energetic sources. The timing and character of reionization depends on the abundance, luminosity, and spectrum of early ionizing sources. If quasars were more abundant at earlier times than currently modeled, the reionization history of the universe is different, with consequences for the thermal state of the intergalactic medium and for the subsequent formation of galaxies in environments that were reionized at different times. JWST is finding quasars and black holes with quasar-scale masses at distances and abundances that exceed model predictions by margins that are growing rather than shrinking as the dataset expands. The black hole formation problem is not a new problem. It is an old problem that JWST has made sharper by extending the observation of massive black holes to earlier cosmic times and finding them there in numbers and sizes that no current model convincingly explains. The cosmic web at scales where it should not be. The large-scale structure of the universe is not random. Galaxies are not distributed uniformly through space. They cluster in groups and clusters connected by filaments of dark matter and gas surrounding vast empty regions called voids. This network of structure, called the cosmic web, is the direct consequence of the small fluctuations in density that were present in the early universe, amplified over 13.8 billion years by gravity. The statistics of the cosmic web, the sizes of voids, the clustering of galaxies, the power spectrum of density fluctuations are among the most precisely predicted and most carefully measured quantities in cosmology. The standard model predicts that structure grows from small to large. The smallest structures form first, then merge and accrete to form larger structures. On scales larger than a few 100 million light-years, the universe is expected to be statistically homogeneous and isotropic, smooth with no preferred direction and no systematic variation in density from place to place beyond the expected random fluctuations. This principle, called the cosmological principle, is one of the foundational assumptions of the lambda CDM model. It is not merely an aesthetic preference. It is built into the mathematical framework used to interpret cosmological observations. JWST, in combination with pre-existing survey data and with the large-scale structure measurements of spectroscopic surveys, is finding evidence for coherent structures at scales that challenge this assumption. Several large-scale overdensities, concentrations of galaxies more massive and more extended than the standard model predicts, have been identified in JWST data in combination with ground-based spectroscopy. The most striking of these are protoclusters, the early universe predecessors of today's galaxy clusters, that appear at redshifts greater than 5 in configurations that imply masses comparable to today's most massive galaxy clusters, assembled in a fraction of the time the models allow. Beyond protoclusters, there are observations of large-scale filamentary structures and overdense regions at redshifts between 2 and 5 that extend over hundreds of millions of light years and contain galaxy populations that are more evolved, more massive, and more chemically enriched than the surrounding field. These structures are not forbidden by the cosmological principle in an absolute sense, because the principle applies statistically over the largest scales, but their existence at the abundances observed implies a density fluctuation, power spectrum that is different from the one the standard model predicts, with more power on intermediate scales than the CMB-based predictions allow. The question of whether these structures represent genuine violations of the cosmological principle, or simply represent the high-density tail of a distribution that is still statistically consistent with homogeneity, is a matter of active investigation. The answer depends on the precise statistical analysis of the observed structures, their abundance, their spatial distribution, and the comparison to simulations that implement the standard model with realistic observational selections. Some analyses claim that the structures are within the expected range. Others claim they are not. The debate has not been resolved. What is not in dispute is that JWST has revealed a universe that is more structured at high redshift than the pre-JWST standard model predicted. The structures are there. Their interpretation is contested. But the existence of the tension between observation and prediction, at a level sufficient to motivate substantial theoretical activity, is itself a statement about the state of cosmological knowledge. The map of the large-scale universe, drawn from JWST data, does not match the map the models predicted. The redrawing of the map is underway. Galaxies that look like grown-ups in a universe of children. The morphology of a galaxy, its shape and internal structure, is not arbitrary. It is the result of its formation, history, the mergers it has undergone, the gas it has accreted, the star formation it has sustained, and the feedback from its central black hole. Galaxies that have experienced violent mergers tend to be irregular or elliptical. Galaxies that have grown gradually through steady accretion tend to be disc-shaped. The proportion of disk galaxies to ellipticals and irregulars at different cosmic epochs is a prediction of galaxy formation models, and it is a prediction that can be tested with imaging observations. Before JWST, the expectation for the galaxy population at high redshift in the first few billion years after the Big Bang was a population dominated by irregular and merging systems, with few well-ordered disk galaxies, and almost no systems with the regular, well-defined structure of today's mature spiral galaxies. The reasoning was straightforward. Disk galaxies form when gas cools and settles into a rotating disk, a process that requires relative dynamical stability. In the violent early universe, where mergers were frequent and gas accretion was rapid and chaotic, this stability should have been difficult to maintain. Regular, ordered structures were expected to be rare in the early universe. JWST has found in its high redshift imaging a a surprising abundance of morphologically mature galaxies at epochs where they should not exist. Multiple studies using JWST's near-infrared imaging have identified well-formed disk galaxies at redshifts of 4, 5, and greater, corresponding to a universe 2 to 3 billion years old or younger. Some of these disks are not merely the early precursors of spiral galaxies. They are morphologically similar to local disk galaxies in their structural parameters, their surface brightness profiles, and their ratios of disk to bulge light. They look, in other words, like grown-up galaxies in a universe that should still be in an early, disordered phase. The fraction of disk galaxies among the overall galaxy population at these redshifts, as measured by JWST, is significantly higher than the models predicted. Pre-JWST simulations of galaxy formation, even the most sophisticated cosmological hydrodynamic simulations run on the largest available supercomputers, predicted a disk galaxy fraction at redshifts above 3 that is inconsistent with what the observations show. The simulations produce these galaxies eventually, but not as many, not as early, and not with the degree of structural regularity the JWST is imaging. The reasons for this discrepancy are not settled. Some theorists argue the disk formation is more rapid and more robust than previously modeled, that even in the turbulent early universe, gas can settle into ordered rotation on shorter timescales than simulations suggested. Others argue that the feedback processes in the simulations are not correctly calibrated, preventing the efficient disk formation that the real universe appears to achieve. Still, others suggest that the structural classifications being applied to JWST images are not directly comparable to the morphological classifications of local galaxies, introducing a systematic bias in the fraction of disks identified. The debate is ongoing and will not be resolved quickly, but the fundamental observation is clear. The universe at 2 to 3 billion years of age contained more morphologically mature, dynamically settled disk-structured galaxies than any model predicted. The universe grew up faster than the models said it should, and this is a statement not just about galaxies, but about the physical processes that shape them, the processes that are apparently operating more efficiently in the early universe than any current simulation captures. The chemical enrichment that arrived too soon. Every element heavier than lithium was produced by nuclear reactions inside stars. This process, called stellar nucleosynthesis, takes time. Carbon, oxygen, nitrogen, the elements that biological chemistry requires, are produced in the cores of stars during their main sequence and evolved phases, and distributed to the interstellar medium by stellar winds and supernova explosions. Iron and the elements heavier than it are produced primarily in supernova explosions and neutron star mergers. The time required for stars to form, evolve, and die, distributing their nucleosynthetic products to the gas from which the next generation of stars forms. This sets a minimum timescale for the chemical enrichment of a galaxy. In the standard picture, the earliest galaxies should be chemically primitive. They formed from gas that was almost entirely hydrogen and helium, with only trace amounts of lithium from Big Bang nucleosynthesis. The first generations of stars, the population 3 stars mentioned earlier, processed this primordial gas and added heavier elements, but enriching a galaxy to the metallicities observed in mature galaxies today requires many generations of star formation and many cycles of stellar death and gas recycling, a process that takes billions of years. JWST's spectroscopic capabilities allow direct measurements of the chemical abundances of galaxies at extreme distances through the identification and measurement of specific emission lines from ionized gas. Different elements produce emission lines at specific wavelengths, and the relative strengths of these lines encode the relative abundances of the elements in the gas. This technique has been applied to JWST observations of galaxies at redshifts greater than 4, 5, and 6, covering epochs when the universe was 1 to 2 billion years old. The results show metallicities, abundances of elements heavier than hydrogen and helium relative to hydrogen, that are higher than models predicted those epochs. Several galaxies at redshifts between 4 and 6 have oxygen abundances that correspond to 20 to 50% of the solar abundance. For a galaxy that has been forming stars for at most 1 to 2 billion years, starting from essentially pristine primordial gas, reaching this level of chemical enrichment requires a star formation history that is more rapid and more efficient than the standard models generate. The specific patterns of chemical enrichment add further information. The ratios of alpha elements like oxygen and magnesium, which are produced primarily in core collapse supernovae from massive stars, to iron, which is produced primarily in type 1a supernovae from lower mass stellar systems on longer timescales, encode the star formation history. High alpha to iron ratios indicate rapid, burst-like star formation. The early galaxies JWST is observing show alpha to iron ratios, consistent with very rapid, intense star formation episodes, more rapid than the models predict for the relevant halo masses and those red shifts. The chemical enrichment problem compounds the mass problem discussed earlier. Not only are the early galaxies more massive than expected, they are also more chemically evolved than expected. They have recycled their gas through multiple generations of stars more rapidly than any current model predicts. If taken at face value, these observations require star formation efficiencies, the fraction of available gas that is converted to stars in each episode of star formation, that are much higher than what simulations produce. Something about the early universe, perhaps related to the properties of dark matter halos at that epoch, perhaps related to the physics of feedback, perhaps related to something not yet in any model, allowed galaxies to build up their stellar masses and chemical inventories far faster than theory said they should. The Rayonization timeline is wrong. The epoch of Rayonization is one of the most important transitions in cosmic history. In the first 380,000 years after the Big Bang, the universe was so hot and dense that hydrogen was fully ionized, existing as a plasma of protons and electrons rather than as neutral atoms. When the universe cooled sufficiently, these protons and electrons combined to form neutral hydrogen, releasing the radiation we observe today as the cosmic microwave background. For the next several 100 million years, the universe was filled with neutral hydrogen gas, a period called the Cosmic Dark Ages, during which no sources of light existed, and the universe was opaque to ultraviolet radiation. Then the first stars and galaxies ignited, and their ultraviolet radiation began to ionize the surrounding hydrogen. The process, called Rayonization, proceeded bubble by bubble, each ionizing source creating a growing sphere of ionized hydrogen around it. Eventually, the bubbles overlapped and the universe became fully reionized, allowing ultraviolet photons to travel freely through the intergalactic medium. By a redshift of approximately 6, corresponding to a universe about 1 billion years old, the reionization process was complete. This timeline is established by observations of the absorption spectra of distant quasars, which show complete Gunn-Peterson absorption troughs, indicating completely neutral hydrogen at redshifts above 6 and progressively more transmission at lower redshifts. JWST is now providing a detailed picture of the reionization process through spectroscopic observations of galaxies and quasars across this epoch. Then the picture it is revealing is more complex than the models predicted. The spatial distribution of ionized and neutral regions during the reionization epoch, the so-called topology of reionization, depends on the sizes, luminosities, and clustering properties of the ionizing sources. If galaxies are more clustered than expected, or if the most luminous galaxies are surrounded by large ionized bubbles, the patchy structure of reionization is different from what homogeneous models predict. JWST observations have found evidence for large ionized bubbles around overdense galaxy protoclusters at redshifts of 7 and 8, where the surrounding intergalactic medium should be mostly neutral according to standard models. These early, the large ionized regions imply either that the ionizing sources are more concentrated and more luminous than predicted, or that the reionization process began earlier than the standard model assumes. Either conclusion modifies the accepted picture of reionization in ways that propagate to other cosmological observables. Additionally, JWST has found that the escape fraction of ionizing photons, the fraction of ionizing radiation produced by stars that actually escapes the galaxy into the intergalactic medium, rather than being absorbed by gas and dust within the galaxy, is variable across different galaxy types and may be higher than assumed in the models for certain galaxy classes. The escape fraction is a critical and poorly constrained parameter in reionization models. If it is higher for the abundant, the low-mass galaxies that dominated the early universe, then fewer galaxies are needed to reionize the universe, and the process could have begun and proceeded more rapidly than the models assumed. The reionization timeline is not dramatically wrong. The basic picture of a universe that transitioned from neutral to ionized between redshifts of 15 and 6 is maintained by the JWST data, but the details, the spatial structure of the ionized regions, the identity of the dominant ionizing sources, the efficiency with which ionizing photons escaped into the intergalactic medium are all being revised, and revisions to the details of reionization have cascading consequences for the star formation history, the chemical enrichment history, done and the large-scale structure of the early universe. The JWST is simultaneously observing in multiple ways. A universe older than it appears. The age of the universe is not a directly observable quantity. It is inferred from the combination of the current expansion rate, the Hubble constant, and the composition of the universe, the proportions of matter, dark energy, and radiation, which determine how the expansion rate has changed over time. In the standard lambda-c dm model with the Planck CMB values for the cosmological parameters, The age of the universe is calculated to be approximately 13.8 billion years. This value is consistent with multiple independent observational constraints, including the ages of the oldest stars in the Milky Way and the timing of globular cluster formation. The Hubble tension introduces an ambiguity into this calculation. If the true Hubble constant is 73 kilometers per second per megaparsec rather than 67, the inferred age of the universe is different. A higher Hubble constant implies faster expansion, which in turn implies a younger universe, approximately 12.5 to 13 billion years, rather than 13.8 billion years. But some of the oldest globular clusters in the Milky Way have age estimates that approach or slightly exceed 13 billion years. If the Hubble tension is resolved by a true Hubble constant of 73, the universe may be barely old enough, or may not be old enough, to contain the stellar systems we observe. This is not the primary claim being made here. The age problem, if it exists at all, is marginal and depends on contested measurements of stellar ages. The more significant point is that JWST's observations of the early universe are providing a picture of a cosmos that assembled its structures, its stars, its massive galaxies, its supermassive black holes, and its chemical enrichment more rapidly than any model predicts. This rapid early assembly is consistent, in a qualitative sense, with a universe that is either older than the standard model calculates, or one that had a different early expansion history that accelerated the growth of structure in its first billion years. The specific form that this early new physics might take has been the subject of considerable theoretical attention. One proposed resolution involves an early dark energy component, a form of energy that was present in the early universe before the CMB epoch and that accelerated the expansion slightly, then data reducing the sound horizon imprinted in the CMB and allowing for a higher inferred Hubble constant consistent with the CMB data. Early dark energy models can in principle resolve the Hubble tension. They also modify the growth of structure in the early universe, potentially producing more massive halos and faster galaxy formation at high redshift, consistent with some of the JWST observations. But early dark energy models face their own tensions with other cosmological observables, particularly the large-scale structure of the universe and the clustering of galaxies, which are sensitive to the growth rate of density fluctuations. A modification that helps the Hubble tension tends to make the large-scale structure problem worse, and vice versa. There is, as yet, no single modification to the standard model that resolves all of the tensions simultaneously. The picture is overdetermined. Too many independent observations point toward a universe that does not quite fit the model, from too many different directions for any single adjustment to the model to resolve all of them at once. JWST is both revealing and sharpening this overdetermination. It is not simply adding one more piece to the puzzle, it is providing high-precision data across multiple cosmological probes simultaneously, and the data from different probes are pointing in directions that are not all consistent with a single coherent modification to the standard model. This is the most uncomfortable position for a scientific field to occupy. A situation where the data is precise enough to rule out the simplest explanations, but not yet sufficient to indicate which of the more complex explanations is correct. The strange spectra of objects that should not emit. What they emit. Spectroscopy is the primary tool of astrophysics. When light from a distant object is spread into its component wavelengths, the resulting spectrum encodes an enormous amount of information: the temperature of the emitting gas, its chemical composition, the velocity of its motion toward or away from the observer, the presence of specific physical processes like shock heating or photoionization. By measuring spectra with sufficient precision, astronomers can determine not just what an object is, but how it works, what drives it, and how it relates to other objects in the universe. JWST's spectroscopic capabilities represent a qualitative advance over any previous infrared instrument. The near-infrared spectrograph, NIR-SPEC, can simultaneously take spectra of up to 100 objects in a single observation, with a wavelength range from 0.6 to 5.3 micrometers, and spectral resolutions sufficient to measure individual emission lines with high precision. This capability has enabled systematic spectroscopic surveys of early galaxies on a scale that was impossible with previous instruments, and the resulting spectra are revealing physical conditions in early galaxies that are genuinely unexpected. One of the most striking results concerns the emission line properties of early galaxies, specifically the ratios of emission lines from different ions of oxygen, nitrogen, and hydrogen. These ratios are sensitive diagnostics of the physical conditions in the ionized gas. The temperature, density, and hardness of the ionizing radiation field. In local galaxies, these ratios fall in a well-defined region of diagnostic diagrams that has been calibrated extensively against models of photoionization by stellar populations and by active galactic nuclei. Early galaxies observed by JWST systematically fall outside the regions of these diagnostic diagrams occupied by local galaxies. The emission line ratios of galaxies at redshifts above 4 are consistently displaced toward higher ionization parameters and harder ionizing spectra than local galaxies of comparable mass. This displacement cannot be fully explained by the known differences between early and local galaxies, such as lower metallicity or higher star formation rates. Some of it may reflect genuinely different stellar populations, perhaps with higher effective temperatures due to lower metallicity or different initial mass functions. Some of it may reflect a contribution from accreting black holes whose emission is diluted enough to make them difficult to classify as quasars, but strong enough to modify the emission line properties of the galaxy as a whole. The most extreme cases are objects that fall in a region of the diagnostic diagram consistent with extreme ultraviolet emission sources unlike any well-studied class in the local universe. These objects have been tentatively categorized as requiring either population 3 stellar contributions, very massive stars formed from metal-free gas, or accretion onto intermediate mass black holes, or some combination of these. The categorization is uncertain because the physical models for these extreme sources are not well calibrated against observations, precisely because such objects are not present in the local universe at comparable abundance. The spectra the JWST is obtaining from the early universe are telling a story about the physical conditions in early galaxies that is substantially different from what was expected. the gas is hotter, more highly ionized, and exposed to harder radiation fields than the models predicted. The sources of this hard radiation are not fully identified. The conditions they produce are unlike those of the local universe, in ways that complicate the use of local calibrations to interpret high redshift observations. And the extent to which these unusual conditions represent a genuinely different physical regime in the early universe, rather than simply extreme versions of processes that are present but subdominant locally, is a question that the current data is beginning to answer in ways that are not yet fully digested by the theoretical community. Gravitational lensing and the objects behind the veil light does not travel in straight lines when it passes through regions of strong gravitational fields. This is a consequence of general relativity. Mass curves space-time, and light follows the curvature. A massive object between a distant light source and an observer acts as a gravitational lens, bending the path of light from the source and producing distorted, amplified, and often multiple images of the background object. The phenomenon of gravitational lensing was first confirmed during the 1919 solar eclipse, and it has become one of the most powerful tools in observational astrophysics. JWST is exploiting gravitational lensing in two complementary ways. The first is the use of massive galaxy clusters as natural telescopes, taking advantage of their gravitational fields to amplify and distort the light of background galaxies into arcs and multiple images that can be studied with much higher sensitivity than would otherwise be possible. The second is the detection of microlensing events, transient brightenings caused by the gravitational lensing of a background source by a compact object in the foreground, which can reveal individual stars and other compact objects at cosmological distances. The cluster lensing program has produced some of JWST's most scientifically significant results. By targeting clusters whose lensing properties have been calibrated from pre-existing Hubble observations, JWST has produced deeply magnified views of galaxies in the first billion years after the Big Bang with a level of detail that allows the study of individual star-forming regions, stellar populations, and chemical abundances in systems that would otherwise be unresolvable. These observations are the source of some of the most extreme early galaxy detections, the most massive, most chemically enriched, and most morphologically regular systems at the highest redshifts. The microlensing program, applied to galaxy cluster fields, has produced a remarkable result. The detection of individual stars at cosmological distances. The most extreme example, a star nicknamed Earendel, and discovered in a Hubble observation but studied in detail by JWST, is located at a redshift of approximately 6.2, corresponding to a distance of approximately 12.9 billion light-years. JWST's observation of this system has provided the most distant direct detection of an individual star ever achieved, at a time when the universe was less than a billion years old. The star's properties, as inferred from its spectral energy distribution, are consistent with a massive, hot, metal-poor object, consistent with an early universe stellar population. The gravitational lensing data are not themselves in tension with the standard model in the way that the galaxy mass and abundance data are. Lensing is a geometric effect, well described by general relativity, drift, and the lensing properties of galaxy clusters are generally consistent with model predictions, but by enabling the detection and detailed study of objects that would otherwise be inaccessible, lensing amplifies the information content of JWST observations in ways that strengthen the tensions identified through direct observation. The most extreme early galaxy systems are found in lensing fields precisely because lensing provides the sensitivity to detect them. The detection of extremely early, extremely massive, extremely chemically enriched systems in lensing fields is not an artifact of the lensing. It is the lensing revealing what was already there. The silence of dark matter in the places. It should speak. Dark. Matter is the dominant form of matter in the universe. It constitutes approximately 27% of the total energy content of the cosmos, compared to approximately 5% for ordinary baryonic matter, the atoms and molecules that make up everything directly observable. Dark matter does not emit or absorb electromagnetic radiation. It interacts only through gravity, which means it cannot be seen directly, but can be inferred from its gravitational effects on visible matter and on the paths of light. The evidence for dark matter is overwhelming. Galaxy rotation curves, which show that stars in the outer regions of galaxies orbit too fast to be explained by the visible matter alone, require a distributed halo of dark matter extending far beyond the visible disk. The dynamics of galaxy clusters, the velocities of galaxies within them, and the temperature of the hot gas they contain require more mass than the visible matter provides. The large-scale structure of the universe, the cosmic web of filaments and voids, cannot form with the observed statistical properties unless dark matter halos provide the gravitational scaffolding within which baryons collapse to form galaxies. The acoustic peaks in the CMB power spectrum are shaped by the ratio of dark matter to baryons in the early universe. Every independent line of evidence points to the same conclusion. Most of the matter in the universe is dark. Despite this, dark matter has never been directly detected as a particle. Decades of experiments searching for weakly interacting massive particles, the leading candidate for dark matter for most of the history of the field, have produced no confirmed detection. The LHC has not produced dark matter particles in collisions. Underground detectors have not observed dark matter nuclei recoiling from dark matter impacts. The expected signal has remained absent across a very large range of possible dark matter masses and interaction cross-sections. JWST cannot directly detect dark matter particles, but it can constrain the large-scale distribution and properties of dark matter halos through their effects on galaxy formation and on the gravitational lensing of background sources. The distribution of dark matter in halos, its density profile, its substructure, and its thermal properties are all encoded in the observable properties of the galaxies it hosts and in the statistical patterns of lensing it produces. What JWST is finding in some of the early galaxy systems discussed previously is that the relationship between stellar mass and dark matter halo mass, the stellar to halo mass ratio, appears to be different in the early universe than in the local universe. Early galaxies appear to be more efficient at converting dark matter halo mass into stellar mass than local galaxies, or equivalently, they appear to sit in dark matter halos that are less massive relative to their stellar mass than local scaling relations would predict. If this is confirmed, it implies either that the halo mass function in the early universe is different from what simulations predict, or that the baryonic physics that converts halo mass to stellar mass operates differently at high redshift. This is not a straightforward statement about dark matter's nature. It could be fully explained by modifications to galaxy formation physics without any change to the dark matter model. But it adds to the accumulated evidence that something about the early universe, possibly related to dark matter properties, possibly related to baryonic physics, possibly related to something not yet included in any model, operated differently from what is currently understood. The silence of dark matter, its continued refusal to announce itself as a detectable particle, is becoming increasingly constraining and increasingly difficult to reconcile with the simplest theoretical expectations. Stellar populations that defy evolutionary models. Stars evolve. This is one of the most thoroughly understood processes in astrophysics. A star's evolutionary track, the sequence of physical states it passes through from formation to death, is determined primarily by its mass and its initial chemical composition. Low-mass stars like the Sun burn hydrogen slowly on the main sequence for billions of years, then expand into red giants and end as white dwarfs. High-mass stars burn more rapidly, evolve through more extreme phases, and end in supernova explosions. The theory of stellar evolution is tested against observations of stars in different evolutionary phases across many different stellar populations and has been validated to a high level of accuracy in the local universe. JWST's observations of stellar populations in early galaxies are revealing systems whose composite spectral energy distributions are inconsistent with the stellar evolution models that work well for local galaxies. Specifically, several high redshift galaxy candidates show spectral features that cannot be reproduced by any combination of standard stellar population models. The UV slopes of these galaxies, the shape of their spectra in the ultraviolet, are bluer than the models predict even for young, metal-poor stellar populations. The emission line equivalent widths, measures of the strength of nebular emission relative to the underlying stellar continuum, are in some cases larger than any current stellar population model generates. These discrepancies have been interpreted in several ways. The most conservative interpretation attributes them to unusual combinations of stellar populations, dose geometries, or ionization conditions that are in principle compatible with existing models, but represent configurations not commonly seen in the local universe. The more radical interpretation is that the stellar populations in early galaxies contain a significant contribution from objects that have no local analog. Perhaps from population 3 stars, whose massive, metal-free nature produces an ultraviolet radiation field harder and more intense than any metal-enriched population can generate. The debate about population 3 stellar contributions is ongoing and is one of the most actively studied questions in the field. JWST cannot yet resolve individual population 3 stars in early galaxies with certainty, but it can measure the spectral signatures of their collective radiation, and the signatures of some early galaxy spectra are consistent with models that include population 3 stars at levels of a few % of the total stellar mass. If confirmed, this would represent the first observational evidence of the specific stellar population responsible for the first chemical enrichment of the universe. Beyond the population, 3 questions. The stellar population discrepancies in early galaxies point to a more general issue. The stellar population models used to interpret high redshift observations were calibrated on local stellar systems and may not accurately describe the physical conditions in the very early universe. The stellar physics of metal-free or very metal-poor massive stars is not fully understood and is not extensively tested against observations because no nearby analogues exist. The models extrapolate to conditions that have no local counterpart. JWST is providing the observations that, for the first time, can actually test these extrapolations, and the tests are revealing discrepancies that suggest the models were not as complete as assumed. The thermal state of the intergalactic medium between the galaxies, filling the vast spaces that constitute most of the volume of the universe, is a tenuous medium of gas called the intergalactic medium. It is not empty space. It is a very low-density plasma of hydrogen and helium, the reservoir from which galaxies draw their gas and into which they expel processed material through stellar winds and supernova-driven outflows. The intergalactic medium is the context in which galaxies exist, and its physical state, its temperature, density, and ionization structure affects galaxy formation in ways that are incorporated into the most detailed cosmological simulations. The thermal state of the intergalactic medium is controlled by the balance between heating, primarily by the ultraviolet radiation from galaxies and quasars, and cooling, primarily by the expansion of the universe and by radiative emission. At the end of reionization, the intergalactic medium was heated to temperatures of approximately 10 to 15,000 Kelvin by the passage of ionization fronts. Subsequently, it cooled as the universe expanded. The temperature-density relation of the intergalactic medium is a sensitive diagnostic of the reionization history, specifically of when reionization occurred and how rapidly the ionization fronts propagated. JWST can probe the thermal state of the intergalactic medium at high redshift through the absorption spectra of background quasars. When quasar light passes through the intergalactic medium, neutral hydrogen absorbs radiation at the Lyman alpha wavelength, producing a characteristic absorption feature. The statistical properties of this absorption, the Lyman alpha forest, encode information about the density fluctuations and thermal state of the gas. By observing quasars at redshifts greater than 6 with JWST's near-infrared spectroscopy, which brings the Lyman alpha feature into the observable wavelength range, it is possible to probe the thermal state of the intergalactic medium, the epoch of reionization. The results from JWST quasar spectra show variations in the optical depth of the Lyman alpha forest that are larger than the standard models of reionization predict. These large fluctuations imply a more spatially inhomogeneous intergalactic medium than expected, consistent with a reionization process that was more extended in time and more patchy in space than the simplest models assume. In some lines of sight, then the intergalactic medium at redshifts of 5 to 6 appears to still contain significant neutral fractions, suggesting that reionization was not complete until later than the standard models predict. In other lines of sight, The medium appears fully ionized at comparably high redshifts. This spatial inhomogeneity is not necessarily a crisis for the standard model. It may simply reflect the natural variation in the density of ionizing sources and the clumpiness of the intergalactic gas. But its magnitude is larger than predicted, and the variations in neutral fraction along different lines of sight are inconsistent with the expectations of the most widely used reionization simulations. In reconciling the Lyman alpha forest observations with the galaxy abundance data and the ionizing photon escape fraction measurements the JWST is also providing requires a more complete and self-consistent model of the reionization process than currently exists. The intergalactic medium is the connective tissue of the universe. Its thermal state during and after reionization influences the formation of low-mass galaxies in ways that are still being quantified. The picture of this state, being assembled by JWST, is more complex, more spatially variable, and more dependent on the details of how individual ionizing sources are distributed than any model current in the field has fully captured. This is not a failure of observation. It is an advance in the precision of the observational constraints and the consequent increase in the demands placed on theoretical models. Galaxy clusters in the early universe. The timing problem. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain thousands of galaxies, enormous reservoirs of hot gas visible in X-rays, and dark matter halos with total masses of 10 to the power of 14 or 15 solar masses. They form through the gravitational collapse and merging of smaller structures, a hierarchical process that in the standard model produces the most massive clusters only at relatively late cosmic times. The prediction is specific. Clusters of a given mass should be exponentially rarer at high redshift than at low redshift. Because the probability of assembling a given mass through hierarchical merging decreases strongly with redshift. JWST has identified candidate galaxy clusters called protoclusters because they have not yet fully collapsed into bound systems at redshifts greater than 7, corresponding to a universe less than 800 million years old. These protocluster candidates are identified through overdensities of spectroscopically confirmed galaxy members in small angular regions. Their inferred masses, based on the velocity dispersions of member galaxies and on the total stellar mass of the system, range from 10 to the power of 13 to 10 to the power of 14 solar masses. If confirmed, these structures represent the most massive known overdensities in the early universe, assembled faster than the standard model predicts. The formation of a structure with a mass of 10 to the power of 14 solar masses by a redshift of 7 requires density fluctuations at that scale that are several sigma above the mean, given the standard power spectrum of initial fluctuations from inflation. Finding multiple such structures in JWST survey fields implies either that the initial power spectrum has more power at relevant scales than the CMB measurement indicates, or that the hierarchical assembly process is more rapid in the real universe than in the simulations, or that the mass estimates from stellar mass and velocity dispersion are systematically overestimated. The last possibility cannot be dismissed. The mass estimates for high redshift protoclusters carry significant uncertainties. Thus, because the conversion from stellar mass or velocity dispersion to total mass depends on assumptions about stellar populations, dark matter fractions, and dynamical states that are poorly calibrated at these redshifts. The most cautious interpretation attributes the observed protocluster candidates to expected but rare high sigma fluctuations rather than to fundamental problems with the cosmological model. But the frequency with which these extreme systems are appearing in JWST surveys is what drives the tension. If each individual protocluster candidate is a rare but acceptable outlier, the rate at which rare outliers appear in JWST survey volumes should still be consistent with statistical expectations. Several analyses have found that the abundance of protocluster candidates in JWST surveys is higher than the standard model predicts at statistically significant levels. The tension is not in any single object, it is in the ensemble. The galaxy cluster formation timeline, as constrained by JWST, is telling the same story as the individual galaxy formation data. Structure in the early universe is more advanced, more massive, and more abundant than the theoretical framework that was the consensus before JWST was launched. The timing problem is not limited to individual galaxies. It extends to the largest bound structures in the universe, and the extension makes it harder, not easier, to attribute the discrepancy to astrophysical processes operating within an otherwise correct cosmological framework. The dust paradox. Pollution. Before the factories were built, dust is everywhere in the universe. It is present in the interstellar medium of galaxies, where it absorbs and scatters ultraviolet and optical radiation, re-emitting the absorbed energy in the infrared. It is present in the circumgalactic medium around galaxies, carried there by supernova-driven winds. It plays a crucial role in astrophysics by providing surfaces on which molecular hydrogen can form, and by shielding molecular clouds from the ultraviolet radiation that would otherwise prevent the formation of complex molecules and stars. Dust is made of heavy elements, silicates, and carbonaceous compounds, and its existence requires that those heavy elements have already been produced by stars and distributed into the gas. Dust takes time to form. The heavy elements must be produced in stellar nucleosynthesis, distributed by stellar winds and supernova explosions, and then processed in the interstellar medium into dust grains. The entire process, from the formation of the first stars to the widespread production of dust grains in the galactic interstellar medium, requires multiple generations of stellar evolution and takes hundreds of millions of years at minimum. The standard models of dust production in the early universe predict that galaxies in the first billion years after the Big Bang should contain relatively little dust, because insufficient time has elapsed for the required stellar processing. JWST's mid-infrared instrument, MIRI, is uniquely sensitive to the thermal emission from warm dust, which peaks in the mid-infrared. Observations with MIRI of galaxies at redshifts greater than 4 are finding, in many cases, levels of dust emission that are higher than expected for galaxies at those epochs. The inferred dust masses in some early galaxies are comparable to those of dusty, infrared luminous galaxies in the local universe, despite the much shorter available time for dust production. The dust paradox mirrors the chemical enrichment paradox. Both require that the early universe processed its gas through stellar evolution more rapidly and more efficiently than the models predict. But dust is an additional constraint, because dust production is a specific physical process with its own efficiency and timescale, beyond the simple fact of chemical enrichment. Even in a galaxy with a high metallicity, the production of dust requires additional physical conditions, specific temperature and density regimes in the interstellar medium, efficient grain growth mechanisms, and survival of the rains against destructive processes like supernova shocks. Several candidate explanations have been proposed. Core collapse supernovae, which are efficient dust producers, could have generated the required dust mass if the star formation efficiency was high enough, and if supernova shocks did not destroy the grains they produced faster than they created them. Asymptotic giant branch stars, which are also efficient dust producers but evolve on longer timescales, are less likely to be responsible in the youngest and most extreme cases. The grain growth in the dense interstellar medium of early galaxies could accelerate the buildup of dust mass beyond what simple models predict. None of these explanations is cleanly confirmed. Each requires specific assumptions about processes that are not well constrained at high redshift, and the dust observations, combined with the chemical enrichment and stellar mass observations, paint a picture of an early universe that was far more turbulent, far more processed, and far more chemically complex than the standard model of galaxy formation predicted. The factories of the universe, the stars, appear to have been running far ahead of the schedule that the models imposed on them. The spatial distribution of star formation is not what was expected. Within individual galaxies, the distribution of star formation across the galaxy's structure provides information about the physical processes driving it. In local disk galaxies, star formation is concentrated in the spiral arms, in molecular cloud complexes distributed through the disk, and in the central regions. The overall rate and distribution of star formation is regulated by the supply of cold gas, by the efficiency with which gas converts to stars, and by the feedback from newly formed stars and central black holes that heat and expel gas. The details of this regulation are encoded in the spatial structure of star formation within individual galaxies. JWST's high angular resolution and infrared sensitivity allow, for the first time, the mapping of star formation within individual galaxies at high redshift. By identifying the positions of bright star-forming clumps through rest frame ultraviolet emission shifted into the infrared, and by using gravitationally lensed systems where the magnification provides additional spatial resolution, JWST has begun to produce resolved maps of star formation in galaxies at redshifts greater than 2. What these maps show is not what was expected. High redshift galaxies are known to be generally irregular and clumpy, with star formation occurring in discrete, massive clumps, rather than the smooth disk distribution seen in local spiral galaxies. This was expected and is consistent with the higher gas fractions and higher turbulence of early galaxies. What was not expected is the specific distribution of star-forming clumps within the galaxies observed by JWST and the relationship between the clump properties and the overall galaxy structure. In several cases, JWST imaging reveals massive star-forming clumps at large distances from the galaxy center, with clump masses and star formation rates that are higher than what the models of clump formation in turbulent disks predict. The clumps, in the most extreme cases, have masses of 10 to the power of 8 or even 10 to the power of 9 solar masses, and star formation rates of tens to hundreds of solar masses per year, concentrated in regions a few hundred light years in size. These clumps, if they are real and not artifacts of projection or lensing geometry, contain star-forming gas at densities and pressures far exceeding those of local star-forming regions. The physical conditions implied by these extreme star-forming clumps are not easily reproduced in simulations. The formation of such massive, dense, rapidly star-forming regions requires either an external trigger, such as a galaxy merger or tidal interaction, or internal instabilities in a very gas-rich and turbulent disk that differ quantitatively from the instabilities simulated in current models. The observations are placing new constraints on the physics of star formation in extreme environments, constraints that will require the next generation of models to incorporate mechanisms not fully present in the current generation. The spatial distribution of star formation within early galaxies is a microscale complement to the macroscale questions of galaxy mass and abundance. Even if the total star formation rate of the early universe is eventually reconciled with the models through adjustments to galaxy formation physics, the internal structure of star formation within individual galaxies represents an independent set of observational constraints that the models must simultaneously satisfy. The data from JWST is accumulating at both scales, and the constraints at both scales are pointing in the same direction. The early universe was more efficient, more structured, and more extreme in its star-forming activity than any current model predicted. The spectral mystery of carbon emission in the early universe. Carbon is one of the most important elements in astrophysics. It is the fourth most abundant element in the universe by mass, after hydrogen, helium, and oxygen. It is the basis of organic chemistry. It is an efficient coolant in the interstellar medium, emitting radiation that allows gas to cool and collapse into dense molecular clouds. Its presence in a galaxy indicates that stellar processing has occurred, that stars have formed, evolved, and distributed their nucleosynthetic products. The detection of carbon in the early universe is therefore both a diagnostic of chemical evolution and a constraint on the star formation history. JWST's infrared spectroscopy has detected carbon emission in several galaxies at redshifts greater than 6, corresponding to a universe less than 1 billion years old. Specifically, the singly ionized carbon line at 158 micrometers, one of the brightest emission lines in the far infrared spectrum of galaxies, has been detected in redshifted form in the near infrared by JWST for galaxies at these distances. The detection of this line is not in itself surprising. Carbon has been detected in the early universe by ground-based submillimeter observatories for galaxies at these redshifts. What is new is the precision and detail with which JWST can characterize the carbon emission and its relationship to other properties of the host galaxies. What JWST has found is that the carbon abundance in some early galaxies, inferred from the strength of the carbon emission lines relative to the total gas mass, is higher than models of early galaxy chemical evolution predict. Carbon is produced primarily in asymptotic giant branch stars, intermediate mass stars in their evolved phases, and involve red stars, massive stars in a specific evolutionary phase. The timescales for AGB star evolution are hundreds of millions of years, which means that if carbon is the primary indicator, the galaxy must have been forming stars for a significant fraction of the universe's age at the time of observation. Finding high carbon abundances in galaxies observed when the universe is less than 1 billion years old places strong constraints on when these galaxies began forming stars. The constraints, in some cases, push the start of star formation back to within the first 100 million years after the Big Bang, a time when the universe was still in or near the cosmic dark ages. This is not impossible within any physical framework, but it compresses the timeline of the cosmic dawn to a degree that requires either very rapid population, 3-star formation and chemical enrichment, or a different stellar population producing carbon more efficiently than standard models account for. The carbon emission detections are part of the broader picture assembled by JWST of early chemical enrichment. Carbon, oxygen, and other elements are all appearing in the early universe at levels that strain the models of chemical evolution. Taken together, these detections are building a case for an early universe that was more chemically evolved, more rapidly processed through multiple generations of stellar evolution, and more structurally complex than the standard picture of the cosmic dawn accommodated. The factories were running faster than the engineering specifications said was possible. Active galactic nuclei at the epoch of galaxy formation. Every large galaxy contains a supermassive black hole at its center. In the local universe, most of these black holes are quiet, consuming little material and producing little radiation. But in the early universe, when galaxies were first assembling and their gas reservoirs were large and dynamically active, central black holes were often accreting at high rates and shining as active galactic nuclei, AGN, among the most energetic and luminous objects in the cosmos. The AGN phase of a galaxy's central black hole is not merely a luminous curiosity. It is a physical process that affects the entire galaxy through what is called AGN feedback. When a supermassive black hole accretes gas at a high rate, it converts a fraction of the accreted mass into radiation with an efficiency much higher than nuclear fusion. The radiation heats the surrounding gas, driving it out of the galaxy in powerful winds. The jets of relativistic plasma that some AGN produce can deposit enormous amounts of mechanical energy into the galaxy's gas, preventing it from cooling and forming stars. A GN feedback is the mechanism that, in galaxy formation models, regulates the mass of galaxies and prevents them from being more massive than observed. Without AGN feedback, models produce galaxies too massive and too star-forming. With it, they produce galaxy populations closer to those observed. JWST is finding AGN at the highest redshifts it can probe, and the properties of this early AGN are creating new puzzles. In several cases, JWST has spectroscopically confirmed broad emission line AGN at redshifts greater than 7, indicating the presence of actively accreting black holes with masses of tens to hundreds of millions of solar masses in a universe less than 800 million years old. The black hole, masses implied by the broad emission line widths, which are calibrated against local scaling relations between line width and black hole mass, are in tension with the galaxy masses inferred from the stellar continuum, The tension is in the ratio of black hole mass to galaxy mass. In local galaxies, the supermassive black hole mass is approximately 0.1 to 0.2% of the galaxy's bulge mass. This tight relationship, called the M-sigma relation, reflects the co-evolution of black holes and galaxies through mutual feedback. In the high redshift A, G, N found by JWST, the black hole masses appear to be a much larger fraction of the galaxy mass, sometimes comparable to or exceeding the stellar mass of the galaxy. The black holes appear to be disproportionately massive relative to their host galaxies, suggesting that black holes grew faster than their galaxies in the early universe, or that the feedback processes that couple black hole growth to galaxy growth operated differently at early times. These overmassive early black holes are not easily explained by any current model of co-evolution. They require either that the seeds of these black holes were unusually massive, consistent with the direct collapse black hole formation scenario, in which entire massive gas clouds collapse directly into black holes without forming stars, or that the accretion onto the black holes was unusually efficient, proceeding at super Eddington rates for extended periods. Neither mechanism is well constrained observationally, and both represent extensions of current models into regimes where the physics is uncertain. The color. Anomalies in distant galaxies. Colors in astronomy are not aesthetic properties. They are quantitative measurements of the distribution of light across different wavelengths, and they encode precise information about the physical conditions in the observed object. The color of a galaxy depends on the ages and temperatures of its stars, the amount of dust it contains, its redshift, and the specific physical processes operating within it. By measuring galaxy colors with sufficient precision across multiple wavelengths, astronomers can separate these contributions and infer the underlying physical properties. JWST's photometric capabilities, combined with its spectroscopic follow-up, allow the measurement of galaxy colors from the ultraviolet through the mid-infrared across a wide range of redshifts. The colors of galaxies at high redshift provide statistical constraints on the distribution of stellar ages, dust contents, and star formation histories across the galaxy population. These constraints are compared to models that generate synthetic galaxy populations based on standard assumptions about star formation, chemical evolution, and dust attenuation. What JWST is finding is a systematic discrepancy between the observed color distribution of galaxies at high redshift and what the models predict. Specifically, there is an excess of galaxies with unusually red infrared colors at redshifts greater than 4, objects sometimes called little red dots in the literature, that are compact, red, and high in luminosity in ways that are difficult to reconcile with standard spectral energy distribution models. These objects appear too compact, too red, and too luminous for their inferred stellar populations, implying either very high dust attenuation in compact systems or a significant contribution from a heavily obscured AGN, or stellar populations with properties not captured by standard stellar evolution models. The little red dots represent a population with no clear local analog and no unambiguous theoretical prediction. They were not predicted by any galaxy formation model as a significant population at these redshifts. Their nature is actively debated. Some analyses favor the interpretation that they are primarily A, G, and heavily obscured by dust, but with A, G, and emission contributing significantly to the observed infrared luminosity. Others favor a stellar interpretation with very high stellar mass densities in compact systems formed through rapid, efficient star formation. Still others propose hybrid models with contributions from both components. The significance of the little red dots extends beyond their individual nature. Their abundance at high redshift, the number of them per unit volume of space, is a further datum in the accumulating case for an early universe that was more active, more structured, and more extreme than predicted. If they are AGN, their abundance implies more supermassive black holes at high redshift than expected. If they are stellar systems, their abundance implies more massive, early galaxies than expected. If they are hybrids, they imply both simultaneously. In none of these interpretations is the abundance of little red dots consistent with the pre-JWST standard picture of the early universe. The tension between models and reality is systematic. At this point in the account of JWST's observations, a pattern is visible. The early universe contains more massive galaxies than expected, more supermassive black holes than expected, more chemically enriched systems than expected, more morphologically mature systems than expected, more dust than expected, more efficient star formation than expected, more extreme AGN than expected. The Hubble constant measured by nearby objects does not match the Hubble constant inferred from the early universe. The large-scale structure shows coherent features at scales that strain the cosmological principle. These are not independent anomalies. They are observations of different aspects of the same universe, and they are all pointing in the same direction. The early universe was more advanced than the standard model of cosmology and galaxy formation predicted. The advancement is not marginal. It is systematic, appearing in multiple independent observations across different physical scales, different physical processes, and different observational methods. In any individual case, the tension can be attributed to one of three things: systematic errors in the observations, systematic errors in the theoretical models, or new physics. Systematic errors in observations are the first thing to consider whenever a result conflicts with well-established theory. The history of astronomy contains many examples of observations that appeared to challenge the standard picture but were eventually traced to calibration errors, selection effect, or subtleties in the data analysis. The possibility of systematic error must always be taken seriously. JWST's results have been examined for systematic errors extensively. The photometric redshifts of early galaxy candidates have been confirmed spectroscopically in many cases, ruling out redshift errors as the source of the early galaxy abundance excess. The mass estimates have been calculated using multiple independent methods with different systematic dependencies. The morphological classifications have been performed by different research groups using different analysis techniques. The spectral anomalies have been identified in multiple independent datasets. In each case, the tension persists under scrutiny. Systematic errors in the theoretical models are the next consideration. Galaxy formation models are not solved from first principles. They involve subgrid physics, parameterized descriptions of processes like star formation, supernova feedback, and AGN feedback that cannot be simulated directly because they operate at scales below the resolution of cosmological simulations. The parameters of these subgrid models are calibrated to match the galaxy population at low redshift. There is no guarantee that the same parameters apply at high redshift, where physical conditions were very different. Modifying the subgrid physics to match the JWST observations is a legitimate response that does not necessarily require new cosmological physics. But the scope of the modifications required is constraining. Multiple independent properties of the early galaxy population are in tension simultaneously, and the modifications required to resolve one tension often exacerbate another. The space of subgrid models that can simultaneously match the mass function, the morphological distribution, the chemical enrichment, the dust content, and the AGN properties of early galaxies is more restricted than the space consistent with local galaxy observations alone. Finding a single, coherent set of modifications that resolves all of the tensions without creating new ones has not yet been accomplished. The systematic nature of the tension is what distinguishes the current situation from a collection of isolated anomalies requiring individual explanations. What the standard model of cosmology actually is, and why challenging, it matters. The lambda CDM model, called dark matter with a cosmological constant, is the theoretical framework within which JWST's observations are interpreted and against which they create tension. It is not a provisional or speculative framework. It is the consensus of the observational cosmology community, supported by multiple independent lines of evidence, including the CMB power spectrum, the large-scale structure of galaxies, the abundance of galaxy clusters, the luminosity-distance relation of type 1 supernovae, and the nucleosynthesis of light elements. Its 6 fundamental parameters have been measured with extraordinary precision. It is, by any reasonable standard, one of the best supported theories in the history of science. Modifying or extending this framework is therefore not a casual undertaking. The modifications must account for all of the existing observations that the model explains successfully, while additionally accommodating the new tensions revealed by JWST. This is a stringent requirement. Many proposed modifications to the standard model that address one tension violate predictions that are already observationally confirmed. The cosmological constant problem, the fact that the observed dark energy density is 120 orders of magnitude smaller than quantum field theory naively predicts, already indicates that the lambda CDM model is not complete. JWST's tensions may be additional symptoms of the same underlying incompleteness, or they may be symptoms of something different. The specific modifications most commonly proposed to address the JWST tensions include changes to the assumed cosmological initial conditions, the power spectrum of primordial density fluctuations generated by inflation to include more power at small scales than the standard scale invariant spectrum predicts. More small-scale power would accelerate the formation of dark matter halos and hence of galaxies, potentially resolving the early galaxy abundance excess. But more small-scale power also produces more small dark matter halos than observed, a problem known as the missing satellites problem. The modification creates as many problems as it solves. Other proposals involve the dark matter model itself. If dark matter is not the standard cold dark matter predicted by weakly interacting massive particle models, but instead has some interaction or thermal property that modifies its behavior on small scales, the galaxy formation process in the early universe would be different. Warm dark matter, fuzzy dark matter, and self-indirecting dark matter are all variants that have been explored. Each has specific predictions that differ from cold dark matter at small scales and has been tested against various observations. None has been confirmed, and the constraints from multiple directions have narrowed the available parameter space. The most conservative response to the JWST tensions is to attribute them to galaxy formation physics rather than cosmological physics, to modify the models of star formation, feedback, and chemical evolution within the standard cosmological framework. This response is coherent and productive, but the comprehensive and systematic nature of the tensions appearing across so many different aspects of the early galaxy population simultaneously is beginning to make the conservative response look insufficient. The data is accumulating faster than the models are adapting. The universe that JWST revealed is not the universe we thought we were living in before JWST. The standard picture of the early universe was a coherent narrative. The first 100 million years produced the first stars, small and faint, their populations gradually enriching the surrounding gas with heavy elements. The first billion years saw the assembly of the first galaxies, small and irregular, degrowing hierarchically through mergers into larger and more structured systems. The first quasars formed, their black holes growing slowly through Eddington-limited accretion from modest seeds. Rayonization proceeded steadily, completing when the universe was about 1 billion years old. The structure of the universe was seeded by inflation, grew under the influence of dark matter and dark energy, and can be described by a 6-parameter model that fits all available observations. JWST has not destroyed this narrative. Many of its predictions remain accurate. The CMB is still well described by lambda CDM. The local universe's galaxy population is still broadly consistent with simulation predictions. The large-scale structure at low redshift still matches the expected patterns. The narrative is not wrong. It is incomplete in ways that are becoming increasingly difficult to ignore. The picture that JWST is revealing of the early universe is a more active, more efficient, more structured, and more chemically advanced cosmos than the narrative accommodated. Galaxies formed faster, grew more massive, built up their chemistry sooner, settled into mature morphologies earlier, and assembled their central black holes more rapidly than any model predicted. The universe, in its first billion years, appears to have been operating at a higher intensity than the theoretical framework designed to describe it had prepared for. This has two implications, and it is important to keep them clearly separated. The first is that galaxy formation physics, the astrophysical processes of star formation, feedback, and chemical evolution requires revision. This is not surprising. Galaxy formation involves complex, multi-scale physics that has always been represented by approximate models. Revising these models in response to new observations is the normal course of scientific progress. This implication is serious but not alarming in the philosophical sense. The second implication is more fundamental. If the galaxy formation physics can be revised within the standard cosmological framework without violating the existing observational constraints, The cosmological model itself may be intact, but if the tensions in multiple observables, including the Hubble tension, the large-scale structure anomalies, and the early galaxy abundance excess cannot all be simultaneously resolved by galaxy formation revisions, then the cosmological framework itself may require modification. A modification to the cosmological framework, to the assumed properties of dark matter, dark energy, or the primordial initial conditions is not a routine scientific step. It is a revision to the foundational assumptions on which the entire observational edifice of cosmology is built. The current state of the field is that it is not yet clear which category the J, W, S, T tensions fall into. The data is pointing toward the need for revision, but the precision of current data is not sufficient to determine unambiguously whether the revision is in the astrophysics or in the cosmology. The next several years of JWST observations, combined with data from complementary facilities, will narrow this uncertainty. The narrowing will either lead to a successful revision of galaxy formation models within the standard framework, or it will lead to the first strong observational evidence that the standard framework itself requires modification. Either outcome is scientifically momentous. Only one of them leaves the foundations of cosmology intact. The edge of the observable and the question of what lies beyond. There is a limit to how far the James Webb Space Telescope can see. It is not an instrumental limit, a limitation of mirror size or detector sensitivity that could in principle be overcome with a larger telescope. It is a fundamental limit imposed by the structure of the universe itself. The observable universe is the region from which light has had time to reach us since the Big Bang. Its current radius is approximately 46 billion light-years, accounting for the expansion of space during the time the light has been traveling. The objects beyond this horizon have existed since the Big Bang, but their light has not had time to reach us, and no observation of any kind can provide information about them. Within the observable universe, JWST can currently observe objects at redshifts up to approximately 13 or 14, corresponding to a universe approximately 300 to 400 million years old. Beyond this, the objects are too faint or too obscure to be detected, even with JWST's sensitivity. The earliest observable epoch, the cosmic dawn, when the first stars and galaxies were forming, is at the edge of JWST's reach, and the observations at this edge are the most uncertain and most difficult to interpret. But what JWST can see, the universe as it was, from approximately 300 million to 13.8 billion years after the Big Bang, is now being surveyed with a depth, the precision, and the breadth across physical properties that no previous telescope approached. The picture being assembled from this survey is the most detailed and most accurate portrait of cosmic history ever achieved. And the portrait reveals a universe that is more interesting, more complex, and more challenging to understand than the theoretical framework that was the consensus at the start of JWST's mission. The implications of this portrait extend beyond the specific anomalies described in this account. Each anomaly is a signal that something is incomplete in the current understanding. The collection of anomalies, systematic in their direction and robust against observational cross-checks, is a signal that the incompleteness is substantial, extending not just to the details of galaxy formation, but potentially to the fundamental cosmological framework within which galaxy formation is embedded. You are looking at the universe right now through these observations, and what you see is a cosmos that is larger than any model perfectly describes, older in structure than any timeline cleanly accommodates, and more active in its early history than any theory fully explains. The James Webb Space Telescope was built to answer questions about the beginning of the universe. It has answered some of them, and in answering them, it has revealed that the beginning was different from what we thought, and that the difference reaches forward through 13.8 billion years of cosmic history to the structure of the universe you inhabit. The question of what the universe actually is, phrased in the most physically precise terms available, is not closed. The telescope has made it more open and more precisely open than at any previous moment. The data exists. The framework for interpreting it is under construction, and the construction is happening against the background of a universe that, as the data continues to arrive, appears to have been built by rules that have not yet been fully read. The light that built the images in this account traveled for billions of years before reaching the detectors of the James Webb Space Telescope. It left galaxies that no longer exist in the form they had when the light departed, passed through space that has expanded enormously in the intervening time, and arrived carrying information about physical conditions that the universe has not repeated since. This light is the most ancient and most distant information ever systematically collected by human instruments. And what it tells us is that the universe we thought we understood is not quite the universe that exists. The tensions are real. They have been checked. They have been cross-verified. They have not dissolved as the dataset has grown. They have, in many cases, sharpened. Galaxies appear in the early universe that should not be there, with masses and structures and chemical compositions that no current model generates in the available time. The expansion rate of the universe cannot be consistently measured from two independent methods that should give the same answer. The largest gravitationally bound structures are more common and more massive at high redshift than the framework designed to describe them predicts. The physical conditions in the earliest galaxies are more extreme than anything seen in the local universe. None of this resolves into a simple conclusion. The data does not say that the standard model is wrong in a way that can be cleanly specified. It says that the standard model is insufficient, that there are features of the universe visible to the most powerful telescope ever built, that the most successful cosmological framework ever constructed does not explain. The distance between insufficient and wrong is where all of the most interesting work in physics lives, and that distance is what the next decade of observations will be spent measuring. The universe is under no obligation to be comprehensible to the minds that evolved within it. But it has, so far, been structured enough and law-governed enough to yield to the instruments those minds have built. The James Webb Space Telescope is the most powerful of those instruments. What it is revealing is that the universe, at the largest scales and the earliest times, is stranger than we knew. The images are precise. The anomalies are real. The explanation is incomplete. That is where the science is. and that is where it will remain for some time to come.